Hi class, this is the video for section 6.2. We're going to be solving systems of inequalities in two variables. So let's get to it. Okay, so we'll have systems of linear and some nonlinear inequalities. The linear inequalities would have this form: ax plus by is less than or equal to c, where you could have any of the other inequality symbols in that place as well. It says if an ordered pair xy makes an inequality a true statement, then xy is a solution. The set of all solutions is called the solution set. The graph of the inequality includes points xy in the solution set. So in other words, there will be, with inequalities, there's not just one or two solutions. There's a whole in these there's going to be like a half plane. So there's going to be an infinite number of solutions that will be in the form of ordered pairs. So systems of linear and nonlinear inequalities. The graph of a linear inequality is a half plane. You're going to have a boundary. The boundary is going to consist of the line, or if it's nonlinear, whatever that graph is. If it's a circle or a parabola, that's going to be your boundary. The solutions are going to be on one side or the other of that boundary. And to determine where that is, we'll select a test point. I will, whenever we can, the easiest test point to use is the origin, 0, 0. I would always use 0, 0. As long as the graph does not go directly through the origin, you can test 0, 0. It's easy to plug zeros into an equation and determine whether the statement is true or false at that point. So here we have the first part A is, this is linear. Here obviously this is not linear. You have x squared plus y squared, which maybe you recognize that's a circle equation there. Let's start with the linear equation. I think probably most of you are most comfortable graphing lines when they're in the form y equals mx plus b. So you can see the slope and the y-intercept. So that's the way I'll demonstrate these ones. So what we can do is solve for, and what we can use here is just, they call it the related equation. So let's just forget about the inequality symbol for right now and think of it as an equals sign. So if I do that, I would have negative 3y equals, and then I'd be subtracting this 2x. 2x, I'm going to move it over to the right side of the equation, my related equation. So I'll slide that over there and make it the opposite. So that would be negative 2x minus 6. And then dividing by negative 3 on each of these terms. I'm not going to show all the work, but I would have y equals, and then negative 2x over negative 3, so two negatives. When we divide, that would be positive 2/3 x, and then negative 6 divided by negative 3 would be plus 2. All right, so this is we're going to call this the related equation. It's in the form y equals mx plus b, making it easy to graph. Okay, so my y-intercept is 2. I'm going to start with a dot there. The slope is 2/3, so up 2 over 3. My next dot would be here. Up 2 and over 3. Up 2 and over 3, or I could go down 2 and left 3. All right, so that's pretty good. Now, the other thing to consider is that your boundary is either going to be a solid or a dashed line. And again, the way that you would determine that, if it includes, so it has the or equal to, that's solid. On this one, it doesn't have the or equal to, this one's going to be dashed. Okay, so we've got a solid boundary going through those points. Now what we need to do is pick a test point. And like I said, as long as your boundary doesn't go through the origin, 0, 0 is the easiest test point. So I'm going to say test 0, 0. So I'm testing that into the original equation. And when I do that, this is real easy to do just mentally. So I'm putting in 0 for x, I'm putting in 0 for y. That makes the whole left side of the equation, or inequality, 0. So I have the statement that's going to read 0 is less than or equal to negative 6. Okay, because 0 here, 0 minus 0 is 0, and then less than or equal to negative 6. Now I just need to determine, is that true or false? 0 is less than or equal to negative 6. Hopefully we realize that that is a false statement. And so I tested 0, 0, which is on this side of my boundary. That was false. that means none of the solutions are on this side. All of the solutions are on the opposite side. So when I shade for my solution, I'm going to shade over here. And so all of the ordered pairs that are in this region would make this inequality true. Okay, so you test your origin, which you usually can do. If that's true, you shade where the origin is. If it's false, you shade on the opposite side. Okay, so we need a boundary, and then we need shading. Next graph. So this one you do have to recognize that it's the equation of a circle, or it's an inequality, but x squared plus y squared equals radius squared. That's the general equation of a circle with the center at the origin. Okay, so center at the origin, and r squared equals 9, which means the radius is 3. I would go 3 each direction. Okay, and again, like I said, because in this one there's no bar under that for or equal to, my boundary should be a dashed boundary. Something like that. And again, our graph does not go through the origin, so let's test the origin, 0, 0. And we're just plugging it into our inequality. And so if I were to put in 0 squared plus 0 squared, that's still 0. So left side is 0, and then I have is less than 9. Okay, so 0 is less than 9. Now in this case, that is definitely a true statement, right? That's true. And so 0, 0, inside the circle or outside the circle. Those are our two options for the solution set. We're either outside or inside the circle. And because 0, 0 was true and that was inside the circle, that means my entire solution set is inside of the circle. Yeah, that wasn't all that good. Let's try it again. Okay, so these are all my solutions inside of that boundary. Okay. All right. To save time I worked these out already and left some work on there. So now what we have on this example is we have a system of inequalities. So we have a line, and we also have, in this case, a parabola. So we have to graph both of those. We have to do a test point in each of these inequalities, and then we want to see where do those shadings overlap. Okay, so starting off, we are going to, I graphed the parabola, just like the related equation, which would be, if we think of that was in blue, the parabola is blue, it's just, y equals x squared. And so that's just our general parabola shape. So origin 0, 0, and then you'd have 1, 1, 2, 4, 3, 9. Those would be points, and then just copying those over the axis of symmetry, I get my parabola shape here. I did graph that with a dashed boundary in blue. Okay. Now at that point down here, I tested in the blue graph, which is the parabola. I could not use 0, 0, okay, because it does go through the origin, so I'm not allowed to use that one. So I picked a different point. I used 0, 1, which is another fairly easy test point. So 0, 1, obviously we're up. We just go up 1, and that's right up in here. So if I test 0 for x and 1 for y in this equation, right? So 0 for x over here, 1 for y, I get the statement that reads 1 is greater than 0. That's a true statement. So in the parabola, my two regions are either inside the parabola or outside. When I tested 0, 1, that was true, so I'd be shading inside of the parabola. I didn't do all of my shading at once, but it would be, for that piece of it, it would be here. But I still have another inequality to test, so I want to test that first, and then, because sometimes you start coloring everything and it gets a little bit messy, so I'm just going to keep a mental note that inside of this parabola, is the solution set of this first inequality. All right, now on the next inequality, this linear one, I just solved for y, put it into y equals mx plus b, y-intercept 4, slope of -1, down 1 over 1, so I get this dashed red line right here. Now in this case, I can use 0, 0 as my test point because it doesn't go through the origin, and if I plug in 0 and 0, 0 plus 0 is 0, 0 is less than 4, that is a true statement, so I want to shade toward the origin, so I'd be shading the open half plane on this side of the line. But overall, my solution set for both of these together are where those shadings would overlap. So if you can visualize inside the parabola and then on the bottom left of this line, the overlapping region is what I've shaded in black right here. Okay, and that is my solution set. And if you want to, as you're going, if it's helpful, you could shade lightly. I don't want to get this all messed up, but you could shade lightly like this for, for your line. We know that it's this part. And then for the parabola, we know that it's inside the parabola, which is like this part. And then you can see the overlapping regions here are where I've darkened in black. So that's what we're wanting to darken up and show that is this region here is the solution region. Any of those ordered pairs in that little odd shape are the solution. Okay. All right, next we have two lines, and again, so for each of these we want to graph them, so I solved y equals mx plus b for both of them. And so the top line, which is in blue, becomes -1/3 x plus 3, so y-intercept is 3, slope is -1/3, down 1 over 3, down 1 over 3, negative slope, so that's our blue line. And the bottom one I did in red, solving that one for y becomes y equals 2x plus 1, and so the y-intercept is 1, the slope is 2, up 2 over 1, and we get this line. So neither one goes through the origin. We can use 0, 0 for both of them. So with the blue line, testing 0, 0, so if I'm putting that in, this was the top one, 0 is less than or equal to 9, and that's a true statement. 0 is less than or equal to 9, so I would be shading below the blue line. Okay, and then in the red line, testing 0, 0, I get the statement that would read 0 minus 0 is less than or equal to -1, 0 is less than or equal to -1, that is false, that's not true. And so where I tested on the red one, now you can see that the origin on that one is actually on this side of the line, and that was false, meaning I would have to go and shade on this side of the red line, the upper left part. Okay, so the overlapping pieces again, if we think about that. So on the blue line, I was shading below, which was like here, all of this stuff here. And on the red line, I was shading this part. Oops. And so our overlapping region would be this part in here, and this is what my solution set is. Okay, so that's graphing systems of inequalities. Okay, the last example is called a linear programming example. Basically, it's a word problem where you use you come up with a system of inequalities, and then the inequalities are called your constraints. It's there's certain limitations on what you have to have in your word problem that you have there. Then there's also another function called an objective function, and this is the one that you want to either minimize or maximize. It's usually money, and so if it's cost, you want to minimize cost. If it's a profit, you want to maximize your profit. And so with our solution set, we're typically looking at the intersection points of our two constraints, and those are going to create a region of feasible solutions, like what we had here. If we have feasible solutions in our solution set region, and there's going to be points of intersection that typically that's what we're going to be testing in our objective function to look for our optimized value. Okay, so I'll walk you through one of these. So it says if the optimal value for a linear programming problem exists, it's going to occur at one at a vertex of the region of feasible solutions. And I'll explain that further as we go. I'm not going to read the steps to you. You can look at those if you would like. Let's take a look at the problem. So here, they did organize our data for us, which is helpful, but let's quickly read through this. A breeder is buying 2 brands of dog food, brand A, brand B, for her animals. Each serving is a mixture of the 2 foods and should contain at least 40 grams of protein and at least 30 grams of fat. So those statements there, at least 40 grams of protein and at least 30 grams of fat, those are going to be our constraints, because that's what we have to be meeting in these in the mixture of these 2 foods. They have to have at least that amount of nutrition in the mixture. Now here, this next statement, brand A costs 90 cents per unit, brand B costs 60 cents per unit. Okay, so that's something else. This is money. And so what we're trying to do is we want to minimize the cost of making this food. So this is going to be our objective function here. Each brand, or each unit of brand A, contains 20 grams of protein and 10 grams of fat, whereas each unit of brand B contains 10 grams of protein and 10 grams of fat. Determine how much of each brand should be bought to obtain a minimum cost per serving. So there's a lot of information in this paragraph, and typically you're not going to have to answer a question just based on a paragraph. The information is going to be organized a little better for you. And so the table is kind of set up here to organize all this stuff up here. So we have brand A and brand B. We're going to say the number of units of brand A, we're just going to assign that as X for the number of units that we use in the mixture of brand A, and the number of units of brand B are going to be Y. Now from this paragraph up above, it told us that each unit of brand A contained 20 grams of protein, and each unit of brand B contained 10 grams of protein. Okay, so we would say 20 times X for the total protein in brand A, and 10 times Y for the total protein in brand B. Okay, and then below this, we know that we have to have a minimum of 40 grams of protein in the mixture. Okay, so that's actually going to be one of our inequalities that we use. And then for fat, brand A had 10 grams of fat per unit, so that's going to be 10 times X, and brand B had also 10 grams of fat per unit, so that's going to be 10 times Y. And this is going to be our second constraint here. The total fat has to have a minimum of 30 grams of fat. Over here, this was our cost. Brand A was more expensive. It was 90 cents per unit, and brand B was only 60 cents per unit. Okay, so we're going to use that as our objective function. So looking here, the constraints. All right, so the constraints have to do with our minimum values we have to have. So total protein, using brand A, which was X, there was 20 grams per unit of protein, and with brand B there were 10 grams per unit. So that was our 20X plus 10Y, and we know that it has to be at least 40 total grams of protein. So that means greater than or equal to, okay, minimum. So it has to be greater than or equal to 40 grams. All right, and then here's our second constraint having to do with fat. And since there were 10 grams per unit of brand A and 10 grams per unit of brand B, minimum has to be 30 grams. This is our second constraint right here. Okay, so those are our inequalities. That's what we would graph. We're going to be graphing those. Okay, then over here, our objective function. Our objective function has to do with the money involved, and that comes from what they told us here. It's 90 cents per unit of brand A, and then brand B is 60 cents per unit. So what we want to do, we're just going to call that cost, and we want to minimize this. So this will be testing our feasible values in this and seeing which one gives us the lowest cost. All right. So on the next slide, I do have this one worked out because there's kind of a lot here. So let's talk through this. Up top, I just recopied these were our constraints. The 20X plus 10Y, which had to be greater than or equal to 40, which represented the protein with that mixture of brand A and brand B. And then 10X plus 10Y has to be greater than or equal to 30, which was the minimum fat content. Now, what I did from here to here, if you notice, every term in here is a multiple of 10. They have a 0. So really, I just divided everything by 10, which is going to make it much easier to graph. They're still equivalent, inequalities. Just dividing both sides by 10, dividing both sides by 10 gives me 2x plus y greater than or equal to 4, and x plus y greater than or equal to 3. Okay, so these are equivalent. I'm going to use these ones. Okay. And then also, I am going to look at the related equation now, because I want to graph these. So just like what I did before, I just solved for y, so I'm subtracting the 2x over, making it negative 2x plus 4. And then here, I'm subtracting the x over as well, and I get this equation. Now let's graph those real quick down here. Okay, so in blue, I'm going to graph this top equation. The other thing is, because we are talking about, x representing the number of units of brand A and then number of units of brand B, there's no negatives involved here, so I'm only going to graph in the first quadrant because we can't have any negatives. So I've got a y-intercept of 4 in that blue graph. Okay, and then I have a slope of negative 2, so I go down 2 and over 1, down 2 and over 1. So that's all I'm going to graph, is just that line segment, because the negative values are not, they don't make sense for the problem. Okay, and then for the second related equation right here, I've got a y-intercept of 3 and a slope of negative 1. So that's down 1, right 1. Now this point of intersection is important. You can see I just intersected the other line segment right there, and down 1 over 1, down 1 over 1, and then I'll just continue. Let's graph that little segment there. We can see where that intersection point is, which appears to be right here at 1, 2. That's going to be important. Okay, and then below, now I'm going to test, because I want to have an area of feasible solutions. So I tested 0, 0 in the blue graph. That gave me false. It gave me 0 greater than or equal to 4. That's false. I also tested 0, 0 in the red graph. This one gave me 0 greater than or equal to 3. Also false. So on both of these, both of these line segments, the origin was false, which means I'm going to shade away from the origin on both of them, okay, which is going to be above. And again, since I'm only working the first quadrant, I would just shade in the first quadrant. But so my region of feasible solutions is going to be, kind of outlining that, but then it's going to be like all of this stuff up here, okay. Now, if you recall what we said before, it said if there is a solution, one of them that's going to maximize or minimize whatever you're looking for, it's going to occur at one of the vertices, okay? So in what I just shaded, this region of feasible solutions, there's this shape, and it keeps going each direction here, but because we're trying to minimize cost, it's not going to be one of these huge values, because, we're talking about minimum fat and protein that we need, but we don't want to put in a ton, because we're trying to keep our costs down. So we just want to meet that minimum value. And so we're going to be checking the vertices. Now the vertices occur here, here, and here. Okay, those are the vertices of our feasible solutions. That's what they mean, okay? And so I'm going to test those, the ones I just highlighted in black. We're going to test those. This is our objective function right here. Okay, I'm going to label that. This is our objective. Right there. Okay, so that's what I'm showing for work below in black here. So I'm testing each of these black dots, these points, these ordered pairs. So the first one right here, that's 0, 4. So I'm putting in 0 for x and 4 for y in the objective function, because we want to see what the cost is going to be to use 0 brand A units and then using all 4 brand B units. Okay, so when I put those in there, okay, and we know that that will meet the fat and protein requirements, because we graphed those and we looked at the intersection of those graphs. When I put those in, I end up with a cost of $2.40 per serving. 90 times 0, 90 cents times 0, and 60 cents times 4. So it would be $2.40 per serving. Okay. Now the next one I'm going to test is this one, and that is the ordered pair 1, 2. So that means 1 unit of brand A and 2 units of brand B. So when I plug those numbers into my cost function, that's 90 cents plus 60 cents times 2 is $1.20, and I add those together, it's $2.10 per serving, so that's less. So right now that's the best. And then if I go to my last ordered pair right here, which is a vertex of my feasible solutions, that ordered pair is 30, so that's what I'm testing here. So that's saying use all 3 of brand A and none of brand B, and so that's going to be 90 cents times 3 plus 60 cents times 0, so that's $2.70, so that's the most expensive, so we can't do that one. We want to use this mixture right here, okay? This gives us it meets our minimum requirements, and it minimizes the cost, and so that's what I'm stating here. 1 unit of brand A, right there, and 2 units of brand B will minimize cost and meet the nutritional guidelines, okay? So that's what's called a linear programming problem. There's quite a bit to it, but it's just kind of a step-by-step process to determine the best. A lot of information, but you're just trying to, in this case, minimize your cost, meet the nutritional guidelines. That's it for this lesson, and you can do the 6.2 homework on Schoology.